So like I said, we're going to be looking in Unit 3 at applications of lines and exponentials, and I don't think we really have them mastered yet, so we're just going to continue working with them as well as throughout the rest of the year. But we're going to start getting into some things that they're useful for. So one of the first, most basic applications you can think of for lines is average rate of change. So you should be asking yourself, well, Mr. McGee, you don't have a line on the board. You have some kind of other weird shape, right? Like, that's definitely not a line. It's some kind of curvy, strange function shape. I didn't give it a name yet. What's like the most common function name that we usually use? F of x. So let's call it f of x. I could call it anything else, but I just want to make it nice and comfortable for you. You're used to f of x, so let's use f of x. Okay, so I kind of just drew a random curvy shape on the board, but once again, I thought we were supposed to be working with lines. Well, average rate of change extends the concept of slope because slope is a rate of change. The thing that's special about lines is that their slope is always the same. Between any two possible points, the rise over run, the little slope triangle dude, is supposed to be the same. If it's not the same, then your line's actually bent and it's not really a line. Does that make sense? So lines have a constant slope everywhere throughout their domain. Other functions, of course, don't. But you can still study them with that same slope idea, and that's what we're going to be doing today. So this is just some random other function curve, and I'm going to be looking at not the slope because it doesn't have a slope, but I'm basically going to be looking at the average slope between different spots. Do you think it's going to be the same everywhere? Well, clearly not, because unless it's straight, if you go up and over, it's going to be different depending on where you go up and over from, right? So I picked some spots on this graph. Let's find the average rate of change. So average rate of change is slope. So you guys remember slope, we did like the, what on top, the vertical or the horizontal part? The vertical, right? Like the rise or the fall. And then on the bottom we had the horizontal part. So you can turn that into a formula, actually. I just didn't do it that way with you guys before because I'm trying to do this in a more pre-formal way besides just throwing lots of formulas at you. Well, I'm going to throw a formula at you today because it's kind of unavoidable. It's really not. It's avoidable. You'll see me avoid using it here. But so vertical, is that y values or x values? It's y values, right? So you should have some like y values. So like if you have 2, then there's a second one and a first one. If you have 2 x values, then there's a second one and a first one. You've got to make sure if you go 2 minus 1, down here you go 2 minus 1. You can't mix and match. Does it matter that you go 2 minus 1? No! You go 1 minus 2 as long as you're consistent on the top and the bottom. And see, I'm not going to be calling things y today. What's another name for y? F of x. So I'm going to say f of x, that x, and f of that x. And I'm going to be writing it like that. Some people also call these x's a and b. What you call them is irrelevant. It's just a name tag. Don't let the name tag freak you out. All this is a slope. But we don't have a constant slope. We're going to have to look at each area, each interval separately. Okay? So I said the first A rock, that's how I want you to write it out, because you don't want to write average rate of change equals every time, do you? Like, this is going to be annoying. So you're going to use the acronym A rock for average rate of change. So first interval I want to consider is between 0 and 4. So let's go look on our graph first. Where's the function at 0? And where is it at 4? So at x equals 0, the first point on our function is right here. Where x equals 4, 1, 2, 3, 4, where's that point on my function? Looks like at the top of this little hump, the maximum up there, right? It's called a local maximum. So if I made the line between those 2 points and found its slope, I'll have the A rock, or the average rate of change for it. So what do you guys think? Is it going to be a positive slope or a negative slope? It's clearly going to be a positive slope. Is it going to be real steep, real flat, or kind of in the middle? I think it's going to be kind of in the middle. If it was steep, it'd be like this, right? This is kind of in the middle, that'd be real flat. So let's start trying to get what value slope is in our head, because that should give us an approximation of the answer here. That's what I want you guys to start thinking about. What is this about before I even do it? These are scaled by ones in each direction. What is it? If it's kind of in the middle, the most middle slope you can get, 45 degrees, is 1 over 1. So that's a slope of 1. Steeper is things like 2 over 1, 3 over 1, 4 over 1, God forbid. Flatter is like 1/2, 1/3, 1/4. So this should be close to 1. You can actually visualize it on here as well. I encourage you guys to draw your lines for your different A-rocks when you're doing your own assignment, okay? So I'm going to draw this guy. Ms. Barnes, what's up? There you go. So there's the line we're talking about. I don't want the equation of the line. I just wanted slope. That's what the average rate of change is. It's an average because it's just between these two spots. If we do any other two spots, it's going to change. Okay? So what's that going to be? So I use my formula up here. I take the y values and put them on top. What's this y value about? We're just going to go about. Ballpark here. 7?
7.
So 7. Change is minus, right? So minus what? What's the other y value? 5, yeah. And then the x values those came from are super easy because they're right here. Which one produced 7?
0.
4. 4 gave us 7,
Oh,
right?
okay.
Which one gave us 5? 0. That's using that formula. Am I really even thinking about the formula very much?
No.
That's using it, but it's just the y values over the x values with a minus in the middle. That's it. So what's the average rate of change turn into? We already ballparked it. Remember we said the slope was going to be like 1 or something like that? Let's see, we get on top 2, on bottom 4, which reduces to 1/2. Looks like my picture is not quite flat enough. It's kind of flat though, right? 45 degrees, I don't think that's quite 45 degrees if we really went and measured it up there. So this makes sense. At least it's positive, right? If we got a negative number, we'd look at that and go, what? So, okay. Let's do a different interval. Instead of the slope between 0 and 4, now I want the average rate of change between 4 and 8. So 4, well, we've already got that point, right? It's the same point. 8 looks like it goes right there-ish, right? So now I'm going to have this line and the slope of this line. I don't care about the whole equation of the line, I just want the slope part. That's the average rate of change. Clearly a completely different slope here, right? It's going to be, instead of positive, negative. Steepness-wise, it looks about the same, doesn't it? Like steepness-wise, let's see how steep though. This tells us specifically how steep. So when I put 8 in, what do I get?
4.
I'm going to say 4. Yeah, I like it. Nice. 4 minus, we already knew what we got when we put 4 in. That's 7. And then on the bottom, what am I going to put? Which way though? You can't mix them up.
8 minus 4.
8 minus 4 is correct. Because what produced the y value of 4? 8. What produced the y value of 7? 4. 4 minus 7 is negative 3. 8 minus 4 is 4. It's a negative slope. Check. 3/4 is close to 1/2. That's a similar steepness value. So, nice. There we go. How about the average rate of change between -1 and 10? So I'm going to erase these green and red things. This guy fixed. There we go. So -1 is over here, right? 10. Isn't that this one?
Yeah. 0.
So this is going to be a pretty boring slope.
So would it be
Because
0
the first
minus
one,
0?
yeah, it'd be 0 minus 0, exactly.
But then we wouldn't even get an answer, so why would we?
Well, we'll get an answer.
But I thought if
What's
it
on the
was
bottom?
over-
Depends which order we went in, right? Here it really doesn't matter. So let's just say we started with -1, that gave us that one, and we ended with 10. That's 0 over -11. What's 0 over anything?
Nothing.
Still nothing. That slope, that average rate of change is 0. We don't have any change happening between those two spots. Does that make sense? That's how you say it. So let's do a couple more. intervals here. Let's do the average rate of change between, let's go 1 and 12. And then let's do, I left out a letter. And let's do the average rate of change between -3 and 9. And let's do the average rate of change between -2 and 0. So if you're watching the video at this point, you want to pause and try these 3 problems out. Remember, you're not going to be exact, but your answers should be real close to mine. I'll put those on coming up. All right, let's look at the average slope or the average rate of change for these guys. So first we're going from 1 to 12, right? So from right here to right there. So we need to find the y values for each one first. So I'm going to say the y value at 1 is approximately 6. So could I start with that? Sure. The formula says start with the second point first, so I guess I won't. But it doesn't matter, as long as you're consistent. So I guess I'll start with the second point, which is 12. What do you guys think the y value is for that? About -2, -3. You guys said -2, so I'll go with that. That's cool. So the y value for the first one is -2. The y value for the second one, 1, is going to be 6. And then we just use these things right here. So what gave us -2? 12. What gave us 6? 1. Put a minus in between for change, because change between things is subtraction. And you've got what you need. So on top we're going to have -8. On bottom we're going to have 11. That's the slope, -8 elevenths. -8 elevenths is close to -11 elevenths, which is a nice 45-degree angle. Let's see if that makes sense. If I connect this point with this point with a line, is the line negative or positive?
Negative.
Clearly negative. And medium slope, that's a medium slope. There you go. Okay. -3 to 9, let's see on that one. So first we're going to look at 9. 9's like right here. That y value looks like 1, yeah? So we're going to go 1 minus. At -3, looks like it's about -4. What gave us 1 was 9. What gave us -4 was -3. Put a minus in the middle. Don't ever forget that minus in the middle, because you have to take the change between the coordinates. So we have some negative action on this problem, which of course is positive. You don't have to write this step, but I'm going to. So yes, that's 5/12. 5/12 is kind of like 6/12, which is 1/2, which is flattish. So we should have a flattish positive line between those two spots. So let's just go back and check. Spot 1, spot 2, line. Is it flattish and positive? Oh man, throw my back out. Yes, it is. Okay, so let's look at that other one. So this time we're going from -2 just to 0. So from here to here, think about the line between those two spots. Is it positive or negative?
Positive.
Positive. Steep or shallow?
Steep.
Steep. So we should get a positive steep number. So let's do it. At 0, the y value is what? 5. At -2, the y value is maybe -3. The x that gave us 5 is 0. The x that gave us -3 is -2. Put a minus, you've got it. So 5 plus 3 and 0 plus 2 is 8/2, which is 4. 4 is positive and steep, just like we expected. So there's average rate of change, or the average slope between any two spots on any function. It doesn't have to be a line to have an average slope. Okay, let's look at one more example. So here's an example with a little bit of context, because we're working on applications. So most of these problems in this unit should have some context. So let me give you a table.
Table.
So let's say we've got lengths and temperatures. I better say what units these are. So let's say, you know what, let's go times and temperatures. So let's go times in seconds and temperatures in what you guys are used to, degrees Fahrenheit. I won't use like the actual science kelvins or something like that, as I should. Okay, so let's say that this table represents the temperature of a rod that we're heating up in a forge. And we've been heating it up, and now we've taken it out of the forge. So at time 0 seconds, that's exactly when we take it out of the forge, and it's really hot. It's like 620 degrees. And then we just let it sit there, and we look at how its temperature is changing in time. So 2 seconds later, it's still 585 degrees. Then 6 seconds later, it's 400 degrees. I bet it doesn't go down that fast. I bet it's like still like 460. And then 10 seconds later, it's gone down to 200. Well, let's make these time intervals the same. Let's say this is 4, this is 6. So what do you guys think? Is this a linear relationship? We've been working with lots of tables. Is it a linear relationship? Is it an exponential relationship? Is it neither of those two things? We could play with our calculator, right? If we go this minus this, that's like 35. If I go this minus this, I'm going to get 40 plus 85, a lot less. It's clearly not linear. It's not decreasing by the same amount each time. But even though it's not linear, we can still apply this concept of average slope or average rate of change. So my question is, first let's do some average rate of changes. What's the average rate of change between, let's say 2 and 6, and then what's the average rate of change between 0 and 4. I just picked random intervals just so we can get the hang of it. And then I want to ask a more detailed question. So I want to say, on what proximal time interval will the temperature of this rod have decreased fastest? In other words, when is it cooling off at the fastest rate? So you guys should already be able to do those first two, right? It's just like the other problem, except instead of a graph, now we've got a table. This is even easier because you can just pull things out of the table. Yeah? So, y values go on top. When I put 6 in, what do I get out?
200.
There's the first y value. I know it's not a y value, I know it's a capital T value, but whatever. When I put 2 in, what do I get out, Miss Porter?
585.
Okay, so that's what goes here. And then on the bottom, what do I put? You guys help me, that's easy. 6 minus 2, done. Y is on top, X is on bottom. That's it. See what happens? We're going to get negative, we might need our calculator, right? You guys might have to help me out. Negative 385, I think, so. Over 4.
Negative 385. Yeah.
Is that right?
Yeah.
What's negative 385 divided by 4? That one I definitely need help with. What is that? Oh, bring one. So it's negative 96.25. And here's what I really want us to do on these contextual problems is put units. What are the units on top? Look at your table. Shouldn't be a hard question. Degrees Fahrenheit. What are the units on bottom? Seconds. So this says between 2 and 6 seconds, this rod is decreasing at an average rate of 96.25 degrees per second. Let's write that out. I want you guys to write that out a few times. That's important stuff. It's not high-level stuff at all. You should be able to read this very specifically. So between 2 and 6 seconds, the rod is decreasing at an average rate of 96.25 degrees Fahrenheit per second. On your problems, I think I gave you 3 in this first assignment like this. I want you to pick one interval for each spot. I don't care which one, and I want you to write it out just like that. Okay, because that's what this really means. That's the way you should be thinking about it. It's very precise. Okay, so now I'm going to do one more random time interval. This time I said, let's look at the rod between 0 and 4 seconds. At 4 seconds, it's 460. At 0 seconds, that's right when we pulled it out of the oven or the forge. It's 620. So then this one was the 4-second one, this one was the 0-second one. So that's going to be negative 240 over 4. Ooh, that one comes out even. Nice. So that's negative 60 degrees Fahrenheit per second. So between 0 and 4 or between 2 and 6, where is this rod cooling down the fastest? It's only cooling down by 60 degrees a second between 0 and 4. Between 2 and 6, it's cooling down at 96 degrees per second. That's faster. Does that make sense? That's a faster decrease. Which one of these lines would be steeper? That one. But of course, they're both going down. So this one would be like totally almost vertical because its slope is negative 96. This one would also be totally almost vertical, but not quite as much because its slope's only negative 60. Okay? So the last question that we didn't answer yet was, on which proximal time interval would the temperature be decreasing the fastest? For those two, we decided between 2 and 6 it was decreasing faster. But I want to know between, is it 0 to 2 that's fastest, where it's cooling down the most? Is it 2 to 4? Is it 4 to 6? How many average rate of changes would I have to do there to compute that? 1, 2, 3. Now, we can of course compute those and get the answers and be real sure about it, right? But since these are changing by the same amount, you can also look at it and just kind of do it in your head or using your calculator a little bit. Where does it decrease the fastest? Well, this change, how much is it? You don't need to know exactly. It's like a little bit, right? Like 30-ish, 40-ish. This one, it's quite a bit, right? You could get our calculator out and say that's like more than 100 degrees down, right? This one, 160? 260. This is like 150-ish down. This is like 35 down. This is like 260 down. So where is it cooling off the fastest or the most? From 4 to 6. That's exactly what we want to say here. You guys got it. Notice I didn't actually have to do those average rate of change calculations. If you can't just see it though, on your problems, you're going to want to actually compute it. And you guys do need lots of practice, I know. So let's see. So if we'd say on, and I want you to write this in complete sentences. So on the interval 4 to 6 seconds, the rod cools down the fastest. We could actually say how much it is. So I think on your problems I actually asked you to do it. So the average rate of change, how much is it? It's 200 minus 460 over 6 minus 4. That's our negative 260 over 2, which is negative 130 degrees Fahrenheit per second. That's how fast it's cooling down at that moment on that interval. Okay? So notice, average rate of change. You can do it from a graph. You you can get the y values. You can get the y values for average rate of change from a table. It's much more common in algebra and math and science in general to pull y values not from a graph or a table. Those are common, but the most common place is to pull them from an algebraic expression, like perhaps that one. How would you get the y values out of this? Because there's one in your assignment you got to be able to do. You plug them in and see what happens, right? If it says find the average rate of change between 7 and 9 on this guy, you're going to need to do f of 7, and you're going to also need to do f of 9 and see what pops out so that you can put those things here and here in your average rate of change calculation. I want you guys to try that yourself. That really should be something you can do at this point. If not, I'm a little concerned. So there you go. That's average rate of change. We'll probably work on it a little bit more next week to review.